Hi everyone, I'm Zhengwei from Rice University. I'm going to introduce our new algorithm, Active Sampling Conscache (ASCS), for online sparse estimation of a trillion-scale covariance matrix. Covariance matrix estimation is one of the most important tasks in statistics and machine learning. For example, in principal coordinate analysis (PCA) and linear discriminant analysis (LDA), covariance matrix estimation is a core part of both analysis. In the recommendation system, it's also important to find the closely correlated items. With the advent of big data nowadays, high-dimensional datasets are pervasive in many daily applications. However, for the high-dimensional dataset with millions of features, it's difficult to estimate its covariance matrix. First, the size of the covariance matrix is huge, which has at least trillions of covariance entries. Just storing the covariance matrix costs at least hundreds of terabytes or even several petabytes of memory. Currently, most of the servers can't store such a huge matrix. But now, we want to ask a much more aggressive question. Can we locate large covariance entries of such a huge covariance matrix using just a laptop? The answer is yes. For example, the DNA Camera dataset has more than 10 millions of samples and features. Its covariance matrix includes 144 trillions of entries. Storing its covariance matrix requires more than half petabytes of memory, while we still want to locate the top 1,000 largest covariance entries on the laptop. To handle this task, our algorithm ASCS only uses 2 GB memory. Moreover, our algorithm is an online algorithm, which means the samples are observed sequentially, and we don't have to save the samples. Therefore, almost any standard laptop is competent to recover the top 1,000 largest covariance entries with the help of our algorithm. Now, we are going to introduce the design of our algorithm ASCS, which incorporates an active sampling process into the Conscache. Now, let's formally define our assumption and problem. The data sample variable y is a d-dimensional vector following the distribution with expectation y and variance sigma y. Assume we observe RID samples of y sequentially, and at each time we can only access one sample. Let x be the vector corresponding to all the covariance variables, and the ex containing all lower diagonal entries of sigma y. The dimension of x is p, where p equal to d multiplied d minus 1 over 2. To simplify our notation, we denote expectation of x ex as mu. Since our dataset is high-dimensional and sparse, so mu is sparse vector with only a few entries are large in scale. Assume with probability alpha, an entry of mu I is larger than u in scale, where u is a constant, and with probability 1 minus alpha, mu I is equal to 0. We call a covariance variable xi is a noise variable if mu I is equal to 0. Otherwise, xi is a signal variable if the scale of mu I is larger than u. Our task is to locate the signal variables of xi. Now, let's unveil the design of ASCS algorithm. ASCS algorithm includes two parts, active sampling and count sketch. First, we briefly introduce the structure of a count sketch and how to use count sketch for sparse estimation of a covariance matrix. Count sketch is a probabilistic data structure widely used to identify heavy hitters in streaming data. A count sketch consists of k hash tables, and each hash table has r buckets. The buckets are initialized at 0 at the beginning. Since the empirical covariance entry mu ti is equal to the summation of xit over capital T. To add mu ti into the count sketch is equivalent to adding xi over t sequentially into the count sketch. Hence, during the insertion period, a covariance variable xi is mapped into the hash tables using k independent hash functions. If multiple variables are hashed into the same bucket, we just add their values. To retrieve the estimate of mu I, we just go back to the k buckets that xi is hashed into and read the corresponding bucket values. The estimate of mu I is equal to the median of the k bucket values. When the signal variable is much larger than the size of the noise variables. Although we may have the hashing collision problems, where a signal variable collides with some noise variables, we can still recover the signal variables easily since accumulation of hashing collisions are almost negligible compared to the scale of the signal variable. However, for the covariance matrix estimation problem, the noises are not so small, and the signal-to-noise ratio is not large enough to guarantee the high accuracy of the count sketch. Therefore, it is natural to think about whether it is possible to reduce the scale of the noises. For example, when we want to insert xt, which is the t-sample of x, into the count sketch, instead of inserting all the xti into the count sketch, if we already know that an xi is very likely to be a noise variable, then we may just ignore xti and do not add it to the count sketch. If we could determine a large number of noise variables, the noise level will be significantly reduced, and we can solve the low signal-to-noise ratio problem. But another problem is how to identify whether a variable xi is a noise variable or not. We may use its estimate to help our evaluation. For example, assume we have already observed t samples. We can estimate mu I by retrieving its value from the count sketch. Here we denote it as mu hat ti. Using this mu hat ti, we can compute how likely the corresponding xi is a noise variable. For example, if the scale of mu hat ti is very close to 0, then xi is very likely to be a noise variable. On the contrary, if the mu hat ti is large in scale, then we suspect that xi is likely to be a signal variable. Using this idea, we developed our algorithm ASCS for the estimation of large covariance matrix. The core idea of ASCS is to filter out the covariance entries that are unlikely to be signals in each run, and only add other covariance entries into the count sketch. First, ASCS spans T0 samples to explore the scale of mu I. After the first T0 samples, ASCS starts to filter the noise covariance entries. At each run, we will design a threshold tau t, and if the estimate of the covariance entry is smaller than that threshold, it will be filtered. and won't be added to the count sketch. Others will be added to the count sketch. As we observe more and more samples, we have more confidence about the scale of the covariance entries. Therefore, we can filter out more and more noise covariance entries as T becomes larger. Now we can see that the key part of ASCS algorithm is how to determine the sampling threshold tau t. If tau t is too large, we can filter a lot of noise variables. However, we may wrongly filter too many signal covariance entries. On the contrary, if tau t is too small, although it's less risky, however, we cannot filter enough noise covariance entries as well. Therefore, we need to achieve a good trade-off. For ASCS, we set tau t as a linear function of t, which involves two parameters, theta and exploration period t0, and we want to determine their values. The theorem below upper bounds the risk of missing a signal covariance entry throughout the sampling process. Assume we can tolerate missing a certain proportion of signal covariance entries. Then we can use this theorem to determine the value of theta and t0. Here we skip the detailed process of finding theta and t0. Please go to our paper for the full process. We evaluate the performance of ASCS on two large-scale datasets, including DNA K-mer dataset and URL dataset. Both have very large covariance matrices. The covariance matrix of the URL dataset reaches 20 terabytes, and that of the DNA K-mer dataset is even larger, reaches half petabyte. To evaluate the performance of our algorithm, we report the mean correlation value of the top 1,000 correlation pairs identified by ASCS and vanilla sketch. The top 1,000 correlations identified by ASCS has very high quality. For example, when ASCS uses 5 hash tables and 100 millions of buckets for each hash table, the mean correlation of top 1,000 correlations identified by ASCS reaches 0.998, which means these correlation pairs are almost perfectly correlated. For the URL dataset, ASCS also finds 1,000 correlation pairs whose average correlation value reaches 0.98. We also compare the performance between ASCS and vanilla sketch. Our results suggest that to achieve the similar performance, ASCS can save 5 times more memory in URL dataset experiments, and for DNA K-mer dataset experiments, ASCS saves 10 times more memory compared to the vanilla sketch. We also evaluate the performance of ASCS on 6 different small-scale datasets downloaded from LibSVM. For each dataset, we randomly subsample 1,000 features. Here, we evaluate the performance of ASCS by comparing the accuracy of locating the top K correlation pairs. Since there is no ground truth of how many signal correlations in a dataset, we just vary the value of K. Again, the figure suggests that compared to sketch, ASCS achieves better accuracy of locating the top K largest correlations, especially when K is relatively small. To conclude, ASCS is a powerful algorithm which significantly reduces the memory usage for online sparse estimation of a covariance matrix. We make it possible to evaluate a trillion-scale covariance matrix using just a laptop, which is not possible previously on most of the machines. Compared to the vanilla sketch, ASCS boosts the performance by filtering the noise variables and raising the signal-to-noise ratio. Moreover, ASCS can be extended to many other applications beyond the sparse estimation of a covariance matrix. When the streaming data have sparse signals, and the samples are IID distributed throughout the screen. We can use ASCS to find signals using sublinear memory. We envision ASCS will be applied in different fields in the future. That's all. Thanks for listening.